Hello everybody. This is the concluding lecture on the series Cache Memory of Module 6 Computer Organization. In this we will be dealing with the write policies of the caches. So far we had looked at memory accesses as if the processor required data to be read from the memory. So what happened? Those were the load instructions. So what happens during the store instructions? Now in the store instruction, the processor wants to store some data. So the closest memory in the memory hierarchy, the closest memory is the cache memory. So the processor would like to store the data in the memory. It stores it in the cache. But you must remember the cache is a subset of what is stored in the main memory. So the corresponding location has to be updated in the main memory also. So how is the main memory locations going to get updated when the cache memory blocks are overwritten by the processor? This comes under the topic write policies of the caches. Okay, so caches are classified as two types: write through caches and write back caches. So again, remember we are now talking about how is the memory main memory going to be updated or written by new data when store instructions come in. Okay, so in write through caches, data that is written by the processor into a particular cache block, okay, is simultaneously written into the main memory. So if there is a store word instruction, that store word instruction causes a particular cache block to be updated or written. The processor writes data into the cache block, and the corresponding to this cache block, there is a location in the main memory because of the mapping. Okay, so this same data is simultaneously written into the main memory also. So this is called a write through cache. So we can see that some of the disadvantages of the write through caches: when you have a store word instruction, every write by the or the store word by the processor to the cache is also accompanied by a corresponding write to the main memory. Now the very purpose of the cache is to make the memory accesses fast. Okay. Now every time the cache is written, the corresponding location in the main memory also, if it is going to be written, it means that the memory access time of the processor during the store word instructions is going to be very large. So comes the next type of cache, which is called the write back cache. Now in the write back cache, there's an extra thing that is called the dirty bit. So each cache block is associated with a single bit, which is called the dirty bit D. So now, how does this data come into the cache block? When the processor accesses the cache and it does not find data in the cache, it goes to the main memory and brings the required data. So a copy of that data is also stored in the cache block for future accesses. Okay. So what is in the cache block is now data that has come from the main memory. Now during the processing, when the program is running, if that data is updated or revised by the processor, then the cache block will be rewritten during a store word instruction. Okay, so a particular cache block will be rewritten or during the store word instruction. So the corresponding main memory location or location corresponding to this cache block also has got to be updated. So we saw that in the write through cache, this updation is done simultaneously, which increases the memory access time. Here we are now going to talk about a dirty bit D. This D is equal to 0 if the cache block has not been written. What came from the main memory is without any change remaining there itself in the cache. So that time D is equal to 0. So main memory, whatever is there, and the cache block, what is there, corresponding mapped place, the same data is lying. But now if the processor changes that data, that is the cache block is now being written, then it makes D equal to 1. Okay, it means that in the cache block, what data is there, and the correspondingly mapped main memory location, what data is there, they are now different because the cache block has been written by the processor. So processor, to indicate this, makes D, the dirty bit D, is equal to 1. It means that the data in the cache block and its corresponding main memory location are now different. It does not write that data simultaneously into the main memory block, unlike the write through cache. It waits. Okay. So we saw during our study on various types of caches that the cache has got a very small size corresponding to the main memory. So at some times the cache block has to be evicted because some other data has to come and be written into that cache block. Okay. So only when a cache block is evicted from the cache will the corresponding cache block be written into the main memory. Okay, but that also there is a condition. If D is equal to 1, remember what D is equal to 1 means? It means the cache block has been written by the processor. Now what is there in the main memory and what is there in the cache are different. So now when the cache block is evicted from the cache, that is it is removed from the cache because some other data has to be written there. Now that data will get lost, no? So what is there in the cache block. So when it is evicted, if D is equal to 1, then the cache block is written into main memory. Only if D is equal to 1, the cache block is written into main memory. If D is equal to 0, what is the meaning of that? The cache block data and the corresponding main memory location data are the same. So there is no need to write it into main memory. So this is what is called a write back cache. Now let us look at the summary of the main points of these two types of caches. Write through caches. When a cache block is written, main memory is written simultaneously. So every cache block write is accompanied by a main memory write, and this makes the memory access times very large. Okay. Now this write through cache does not require the use of a dirty bit, but it requires more main memory than write back caches because everything has to be written back into the main memory. Okay. Now if you look at the write back cache, when a cache block is written, main memory is not written simultaneously. Okay. A cache block write is not accompanied by a main memory write. It is not written simultaneously. It requires the use of a dirty bit D. Alright. When a cache block is evicted from the cache, only if D is equal to 1, then cache block is written into main memory. Okay. Only when the cache block is removed from the cache because some other data has to come into the cache, then only if D is equal to 1, then that corresponding cache block is written into the main memory. This reduces the memory access times compared to the write through cache. Alright. So it also requires less main memory than write through caches. So you can see that the write back caches are more practical than the write through caches. They're faster. Alright. So modern caches are the write back type because of the lower memory access times. Now to understand this a little better, let us go through an example to understand the difference between the write through and the write back cache. Now this is an example. This is an example of an 8-word cache. We are going to talk of a direct map cache, an 8-word cache. It has a block size of 4. What is block size? That is small letter B. That is the number of data words in a block. That is 4. Okay. So what will be the number of blocks? The number of blocks is the channel capacity, cache capacity C. Cache capacity C is what? 8 divided the block size by the block size 4. So what is that? 8 divided by 4, that is equal to 2. And since this is a direct map cache, S is equal to B is equal to 2. That's all right. So look at the way the cache has been constructed. So let us see two sets, set 0 and set 1. S is equal to 2. So in each set, there is one block. In that, the block size is equal to 4. That is the number of data words in that block is equal to 4. So let us see again. The number of sets is equal to 2, 0 and 1. The number of blocks and the number of sets are the same. So B is equal to 2. Inside each block, there are 4 data word locations. You can store 4 data words here. That is why we say that the block size, so the number of data words in each block is equal to 4. Now for addressing this, the memory address, our 32-bit memory address can be divided into byte offset. We already know what is byte offset. Byte addressable memories require the last 2 bits for addressing the bytes. Okay, 0001, 1011 addresses the 4 bytes in the 32-bit data. Now block offset, this is a new thing. Block offset refers to the address of each of the data words in a particular block. Okay, so if block offset is 00, it means this location. Okay, 01 this location, 10 this location, 11 this location. Similarly for this set, if you are addressing this set, this is 00 block offset, 01 and so on. Now what is this set? Set bits we know. Set, there are only 2 sets. So we need only 1 set bit, because if that set bit is 0, it means we are addressing set 0. And if that set bit is 1, it means we are addressing set 1. Okay. The remaining bits are the tag. Now look at this. piece or the snippet of code. There are 4 store word instructions that are coming in simultaneously in the program, one after the other in the program. So the first store word says go and store. You remember the store word instruction. This is the base register. This is the base register and this is the offset. This is the base register and this is the offset. The base register is 0. So 0 plus whatever is this offset. So 0 plus 0, it refers to this data word. Okay. Now this 0 plus C, it refers to this location. 0 plus 8 refers to this location. 0 plus 4 refers to this location. So the first store word instruction stores the word in this location. Okay. The second one stores it in this location. The third one stores it in this location and the fourth one stores it in this location. So since there were 4 locations inside the block, okay, then inside set 0, all these 4 things could get stored. Now, when the storage is happening in the cache memory, or the writing of the cache memory is happening, there is no simultaneous write back into the main memory if the cache is write back. But if the cache is write through, each and every one of these stores will require 4 main memory writes also, reducing the memory access, increasing the memory access time. So every time a location is written, there is a corresponding main memory write, increasing the memory access time. But write back does not require. Okay, these 4 locations will get written and the main block, main memory need not be written. That doesn't. It will require a main memory write only if this block is evicted. All these 4 things are evicted from the cache and some other data is going to replace it, so that we don't lose this data. Then there will be a main memory write. Only if this block is evicted from the data, then only you have a main memory write. So this reduces the memory access time compared to the write through cache.